And now invite our first speaker, Amy Dale, who has given us a title, There's Plenty of Room at the Bottom of the River, Modeling Pollution from the Nanotech Revolution. Welcome, Amy.
Thank you. In 1959, Nobel Prize-winning physicist Richard Feynman gave a groundbreaking talk titled There's Plenty of Room at the Bottom, in which he challenged scientists to discover means of manipulating matter at the size scale of individual atoms and offered $1,000 to the first person who could fit the entire text of the Encyclopedia Britannica on the head of a pin. This prize was claimed by Tom Newman in 1985. Today, nanotechnology has become a multi-billion-dollar enterprise backed by such industry giants as Samsung, Nokia, and Hewlett-Packard. Everyone in this room uses nanotechnology every day. It's in your cell phones, your laptops, and your cars. Importantly, however, it may also be in your socks and shampoos, your makeup and sunscreen, and your food. These low-tech uses of nanotechnology involve the use of metal or metal oxide nanoparticles, and globally we now produce up to 300,000 metric tons of these tiny particles each year. The problem is that 60 to 90% of what we produce is eventually going to end up in the environment, and some of the metals commonly found in nanoparticles, such as silver, copper, and zinc, are some of the oldest known environmental pollutants. For my first project as a Ph.D. student, I modeled the complex chemical transformations that one particular nanoparticle, nanosilver, undergoes in the lake beds and riverbeds, where it accumulates once it escapes into the environment. This work revealed that nanosilver will react with naturally occurring sulfur-containing compounds in a way that actually reduces its toxicity over time. Unfortunately, this process also increases the particle's lifetime, leading to its persistence and accumulation. This model provided valuable insights, but it fails to capture the big picture. To bridge this gap, I'm currently developing a watershed-scale model in collaboration with the US Environmental Protection Agency. This work combines data from elevation maps, agricultural surveys, meteorological records, and more to describe water, sediment, and nanoparticle transport throughout an entire watershed. This model serves both a theoretical and a practical purpose. On the theoretical side, it acts as a proof of concept, showing us that we can use traditional modeling frameworks to model nanoparticles, even though this new class of pollutants doesn't always behave like conventional pollutants. On the practical side, it allows us to answer several key questions. Will nanoparticle production now or in the future lead to environmental concentrations of metals that exceed toxicity thresholds or regulatory limits? What are the major sources of nanoparticles in the environment? And finally, how can we most effectively manage nanoparticle risk? By asking these questions early and often, we aim to inform industry and government decision-making for the safe and responsible adoption of this promising new technology. Thank you.
Thank you, Amy.